We're going to finish up here with chapter 7 with another look at determinants. This is pretty short here. We're going to look at some of the properties of determinants. And some of these, I don't know if any of them are intuitive. I think you could see them after talking through them a little bit. Now, instead of reading this screen to you, I'm going to just do the example and we'll talk through them one at a time. So we have this matrix A here, and we just want to, let's see. Oh yeah, we're doing property 1. So property 1 says if it's an upper triangular form. This just means that you have that diagonal and everything below it is 0. And so what they're saying here is that if you have that case, then yeah, all you're going to get is the properties of the main diagonal. So we just multiply this down. So here we go. We're in upper triangular form because everything else is zeros. If we multiply down the diagonals, that's all we need to get our value. We don't have to do the up. And the reason is because it's just going to be those zeros are going to repeat. It's just the math. That's all there is to it. So again, I don't know how useful this is, but we're going to talk through it here. So if you're in this upper triangular form, because these would repeat, when all you have to do is the downward diagonal to get the determinant. Okay, so the second property says if you interchange rows, you change the sign. And the reason for that is going to be that if you flip the rows around, you're going to change the diagonals. So remember, the way the determinant is formed is you go down on the diagonal, subtract up on the diagonal. Well, if you interchange that, you're flipping the order. So by interchanging rows, you change the sign of the determinant. Okay, again, this one isn't necessarily intuitive either, but it's actually going to come from the idea. It's just the math. By having 2 rows or 2 columns that repeat, then what's going to happen is you're going to get repeats on the back end. You're going to get repeats on the subtraction end. And so they're going to make everything cancel out. So 2 rows or 2 columns that are identical, the determinant is going to equal 0. Okay, yeah, a row or column equaling 0 is going to make a 0 determinant. I think that makes pretty much the same idea. It's just the math. You did your downward diagonals, you do your upward diagonals. If that whole row or column is 0, it's going to make the math just, it's going to have everything filled with at least one 0, which will make the final product 0. This one's clever and a little interesting. It turns out that the determinant of a matrix and the inverse of a matrix have reciprocals for their determinants. Now, I'd have to think through why that is. That's pretty clever. So normally when you think of a reciprocal, if you had 2, your reciprocal is 1/2. Well, it turns out that the reciprocal of a matrix and its inverse have reciprocal values for their determinants. So that's pretty interesting to me. Maybe not to you. Okay, let's see. Yeah, if you multiply any row or column of a matrix by a constant, the determinant is going to be multiplied by that same amount. So we're multiplying here. Row 1 is being multiplied by 2. It's going to do the same to the determinant. The final value of the determinant is going to get multiplied by 2. And again, this is just the math of how this works. Now, without spending a lot of time in the world of matrices, I don't know why all these would be all that helpful, but there is going to be one application that they're going to give us here with this example. So if we were trying to use Cramer's rule to solve this system of equations, what we could see here instantly is I have 2 columns that repeat. So because these columns repeat, I could crunch the math on this determinant and find out that I've got a problem, but I know from property 3 that if I have 2 repeat columns, the determinant is going to be 0. Now, what good does that do me? Well, if I know the determinant of a matrix is 0, then I know it's going to be either no solution or infinite solutions, but I can't tell which one. So by recognizing these repeat columns, I could instantly stop and just say, okay, this isn't going to work. I know it's either no solution or infinite solutions, and I'm going to have to go back to the elimination approach to try to solve this. Just a quick step with the elimination. If you just worked with the first equation and the bottom equation, try to eliminate that, you instantly get down to 0 equals -6, which is not true, so we get no solution. So again, I don't work with a lot of matrices, so I don't know how often these principles are of all that value, but they're giving us one application here. These repeat columns, two of the same column, tell us that we're going to get a determinant of 0, which would instantly tell us we don't have any math to do. So instead of trying to do the math, we'd instantly see, well, okay, this is either no solution or infinite solutions. We check that by the elimination approach and we find out it's no solution. Okay, short section. Hope that makes some sense.